You're listening to EUAudio. Listen, learn, lead. Bicomponent fibres. Beyond animal hides and early felt clothes, humans have been weaving for at least 30,000 years, with the ancient Egyptians using linen and the Chinese inventing silk. Now, innovations in fibre technology are creating opportunities for the use of smart materials in industrial applications. Before the start of the first industrial revolution in the middle of the 18th century, weaving was a manual task performed by hand at home to create fabrics and textiles to make clothes. The invention of the automated spinning machine allowed cotton and woolen fibres to be spun into a continuous yarn or thread, which could then be woven into cloth. It was over 100 years after this, in the early 1880s, that the inventor Joseph Swan created the first artificial fibre using cellulose harvested from tree bark. The following 100 years saw the invention of other synthetic fibres, with everything from viscose rayon, cellophane, nylon and polyester being used to transform the global textile industry. More recently, in the 1960s, the chemical company DuPont, famous for inventing polymers such as neoprene, nylon, Teflon, Kevlar and Lycra, invented the first bicomponent fibre, which it used to make women's stockings. A bicomponent fibre is a fibre made from two different materials with different chemical or physical characteristics. These materials are combined into a single extrusion using a spinneret, the same tool used to make conventional synthetic fibres. It works a bit like Play-Doh, with the melted polymer entering the top and being forced through a needle-like nozzle at the other end, which is then cooled by air or liquid into a continuous filament. The only difference between conventional fibre and a bicomponent fibre is that multiple streams of different polymers combine to make a single filament. In this way, engineers can tune the fibre to use a different core material and a different sheath material, for example. The different shrinkage rates of the materials work to self-crimp the fibre to form a strong adhesion. As well as being extruded next to each other, side by side, the cross-section of the filament can take any shape. One of the more complex structures are called matrix fibril, or islands in the sea fibres. It sounds complicated, but the cross-section essentially looks like a pepperoni pizza from the top, small circles of pepperoni in a sea of cheese. The beauty of this method is that once woven into a fabric, the textile can be treated with a chemical, or sometimes even washed with water, to remove the so-called cheese, leaving just the very fine strands that make up the fibre. Whichever cross-section they take, bicomponent fibres offer engineers material characteristics that would simply not be possible with other natural or single-polymer synthetic fibres. These properties range from the material's resistance to water, fire, stains and chemicals, to its low weight and high strength. Bicomponent fibres are not new. They've been around for 50 years, with brands such as Alcantara becoming popular. However, with the advent of micro and nano fibres and more reliable and precise manufacturing techniques, these fibres open up opportunities for advances in a variety of industrial applications. In industry, these fibres can allow finer filters to be made that can eliminate more impurities in fewer passes. This could mean filtering acidic chemicals or liquids that would etch traditional polymers, removing impurities from water and paint, or even filtering more particles in air compressors for clean rooms. For the medical sector, which typically uses non-woven fibres to create items such as isolation gowns or surgical masks, these fibres offer a way of adding durability to the materials to avoid things like tears or material failure during prolonged use. In medical packaging, the porosity of the material could be tuned to allow contactless gas sterilisation. In electronics manufacturing, bicomponent fibres could be used to eliminate the need for heat shielding or additional sheathing to protect cabling from heat damage and cuts, or to improve cooling efficiency while ensuring the product remains lightweight and durable. In general, such innovations could even offer a new lease of life to old components, allowing manufacturers to refurbish or recondition parts to add functionality and performance gains at the end of the product's useful lifespan. Whatever applications they develop, there's a lot manufacturers can learn from a textile industry that can trace its humble origins back some 30,000 years. EUAudio is brought to you by EU Automation.